Right now, as you're listening to me, your body is doing something absolutely miraculous. You're breathing. And yeah, it feels simple, right? Almost automatic. But the actual journey that air takes from the world around us to the deepest parts of ourselves, well, that's an incredible story of biological engineering. So let's follow that journey together.
Take a normal, relaxed breath. The amount of air you just moved is about 500 milliliters. Now, what does that even mean? Well, picture a standard water bottle. That's about how much air is flowing in and out of your lungs with every single quiet breath. And get this, it happens around 12 times every minute. Just a constant, steady rhythm keeping you going.
So here's our game plan for this journey. We're going to break it down into 5 key stages. First, we'll look at breathing by the numbers. Then, we'll check out the highway that brings blood to meet the air. After that, we'll get into the physics that makes it all work, watch the actual exchange happen, and finally, see that precious oxygen get delivered to your body's tissues.
Okay, so we've got that 500 milliliter number for a normal breath, but that's just the start of the story. What are our lungs really capable of? To figure that out, we've got to dive into the numbers.
First up is this idea of lung volumes. And you really shouldn't think of this as just one single number. It's way more dynamic than that. Think of it more like the water level in a reservoir. It's always changing depending on if you're breathing normally, taking a huge gasp of air, or pushing every last bit out.
So, the most basic measurement, the one you're doing right now without even thinking about it, is called tidal volume. That's that easy 500 milliliter breath we just talked about, flowing in and out just like the tides. Simple enough.
All right, try this with me. Take a normal breath in. Now hold it and keep breathing in. Force as much extra air in as you can. That extra bit you just inhaled, that is your inspiratory reserve volume. It's the deep breath power you have waiting in reserve for when you need it.
But here's something wild. Your lungs are never actually empty. Even if you exhale as hard as you possibly can, there's always a good amount of air left in there. We call that the residual volume, and it's absolutely critical. It basically acts like a little air splint, keeping all those tiny, delicate air sacs from collapsing on themselves. Pretty cool, huh? So when you look at these numbers side by side, something pretty amazing pops out. Our everyday, quiet breathing barely scratches the surface of what our lungs can do. That 500 milliliter tidal volume is tiny compared to the 1,200 milliliters of residual air that's always in there. It just shows you how much backup capacity we have. Okay, but there's a catch. Not all the air you breathe in actually gets to do the important work. Some of it just hangs out in the pipes, your nose, your throat, your bronchial tubes, and never makes it to the air sacs where the real action happens. We call this dead space. It's air that's just along for the ride. All right, so the air is in. Job done, right? Not even close. Air sitting in your lungs is totally useless unless we can get blood to it. And that happens on a very special, very efficient biological highway, the pulmonary circulatory system. Now, this isn't your body's everyday plumbing. The system that pumps blood to your toes is a high-pressure deal. The pulmonary circuit, it's completely different. It's a low-pressure, high-flow superstar. Its arteries are huge, which lets them easily handle every single drop of blood the right side of your heart pumps out. It's all designed to get that deoxygenated blood to the lungs for one reason and one reason only: to pick up oxygen. Okay, before we see that magical moment where oxygen jumps from the air into the blood, we got to talk about the fundamental law of physics that makes it all possible. It's the engine behind the entire process. Just look at this. It's a really simple but incredibly powerful idea. Imagine the air is a mix of different gases, right? Oxygen, nitrogen, carbon dioxide. Each one of those gases behaves as if it's the only one in the room. It just does its own thing, exerting its own pressure, totally ignoring all the other gases around it.
So this idea has a name, Dalton's law, and the pressure that each individual gas exerts is called its partial pressure. Now, here is the crucial takeaway, the one rule you need to remember. Gases always move from an area where their partial pressure is high to an area where it's low. Always. That simple downhill slide is the driving force for everything that's about to happen.
Okay, the stage is set. The air is in the lungs. The blood has arrived. We know the rules of pressure. It is time for the main event, crossing the air-blood barrier.
This whole process is called external respiration, and it's where the magic really happens. This is the moment that deoxygenated blood, full of CO2 waste, gets transformed into oxygenated blood, ready to fuel the body. And it all goes down in these millions of tiny air sacs called the alveoli.
So why does this swap happen so perfectly? It's all about those pressure gradients. The fresh air you just breathe into your alveoli is packed with oxygen, so it has a high O2 pressure. But the blood arriving from your body has already dropped off its oxygen, so its O2 pressure is low. It's a no-brainer. Oxygen just flows downhill, from the air into the blood. And the exact opposite is true for carbon dioxide, which flows out of the blood and into the air to be exhaled.
And here you can see it happening. That deoxygenated blood arrives, unloads its cargo of carbon dioxide into the alveolus, and at the exact same time, it scoops up fresh oxygen. You can see the red blood cells literally changing as they get ready to make their journey back to the rest of the body. But hold on, the journey is not over yet. All that oxygen-rich blood isn't doing any good until it actually delivers its cargo. And that brings us to the final, crucial leg of the journey: internal respiration. This is the final destination. This is the exchange that happens deep inside your body, where your tiniest blood vessels meet the individual cells of your muscles, your brain, your organs. Honestly, this is the whole reason we breathe in the first place. And check it out, the pressure gradients have completely flipped. Now, the blood arriving in the capillaries is loaded with oxygen, so its O2 pressure is high. But your tissue cells have been busy working and using up oxygen, so their pressure is low. Again, oxygen just flows downhill, out of the blood and into the cells. At the same time, those hardworking cells have created CO2 waste, making its pressure high, so the CO2 naturally flows into the blood to get carried away. So, after dropping off its oxygen and picking up the carbon dioxide trash, that blood is now deoxygenated again. It makes its way back to the right side of the heart, which gives it a push right back to the lungs, and the whole incredible cycle starts all over again with your very next breath. So just think about that. From a simple breath of air, to the invisible laws of physics, to an exchange happening deep within your cells, this entire mind-bogglingly complex journey happens about 12 times a minute, without you ever having to think about it. It's a constant, perfect dance between physics and biology. The next time you just take a breath, maybe you'll think about this incredible journey and just appreciate the silent, brilliant work your body is doing for you right now.